In this video, I'm going to be going over the free response section of Exam 2 for Dr. Collini's Chem 2380 class. So the first question is, using proper curved arrows, draw the resonance structures of the following molecule, and then don't worry about negative or negligible contributors. So to draw resonance structures, I think it's helpful to pay attention to lone pairs, double bonds, and positive charges. For me, it makes the most sense to move the electrons next to the positive charge first. So I'm going to go ahead and do that. So we can move these electrons up here to fill in that positive and create a new positive down here. So that will look, so that molecule will look like this. And then from there we can do the same thing. We can just move this double bond to fill in where the positive charge is. And that structure will look like this. And then the last structure, we can have one of the lone pairs on the oxygen resonate down to fill in the positive charge. And when we do that, the structure looks like this. And then to complete the resonance structure, we put all the resonance structures in brackets. So the way that I graded this question, in case anybody is curious, is I gave a check mark for each correct arrow. So that would have been 1, 2, 3. I also gave a check mark for each correct positive charge. So if you place the positive where it needs to be, that's another 3 check marks. And then I also gave a check mark for correct structures. So 3 structures drawn correctly. And then lastly, I also gave a check mark for each double-headed arrow. You had to draw them correctly. You couldn't draw equilibrium arrows. It had to be resonance arrows. So you get a check mark for each of those. And then if you drew your brackets correctly, you get 2 check marks. A lot of people drew their brackets like they only got one side, but they forgot the other side, or they put it around here, but they forgot to include this. So I gave you I gave you 1 check mark instead of 2. So each check mark was worth half a point. So this question totaled, the total points were 7 points possible. Question 2 says, comparing the 2 molecules below, the lone pair on one is more likely to react as a base than the other. So which one is more likely and why? So let's think about the basicity of the 2 lone pairs. In both molecules, the lone pair is capable of resonating into the ring. So what I mean by that is we could have this lone pair form a double bond here, create a lone pair there, and then if we had a lone pair here, it would look like that with a double bond here, and this would be gone. And then this lone pair could resonate, moving this into a lone pair, and this would be gone, and so forth. So the lone pair can resonate into the ring, but whether or not it's actually going to is determined based on whether or not the molecule is aromatic or anti-aromatic. So to determine if it's aromatic, we need to think about the rules that we have for aromaticity. With both molecules, we can draw pi orbitals on every carbon within the ring. That's true for here too. If you draw on either side of the double bond and wherever there's a lone pair, it's possible that the ring is fully conjugated. However, the aromatic molecule must follow the 4n plus 2 rule. So in this case, we have 2, 4, 6 electrons. So that follows the 4n plus 2 rule. This one has 2, 4, 6, 8, which does not follow the 4n plus 2 rule. And again, if you need a refresher on that, 4n plus 2 needs to be equal to the total number of electrons that you have in your conjugated system. So for molecule 1, that would be 6. And then you solve for n. So 6 minus 2 is 4. And then over here we have 4n equals 4. Let's divide by 4 on both sides, n equals 1. N is an integer, so this matches it follows the rule. If you were to do that same thing with the molecule 2, we could set up that same equation. So in this case we have 2, 4, 6, 8. So 4n plus 2 equals 8. Subtract 2 from both sides. 6 is equal to 4n. Divide by 4, divide by 4. N is equal to 3 over 2, which is not a whole number integer, so this is not going to follow the rules for aromaticity. So because of that, if the lone pair here were to enter into that pi orbital and become delocalized, this molecule would actually be anti-aromatic, which is less stable. So it's better for that lone pair to instead occupy a hybridized sp3 orbital to avoid anti-aromaticity. So let's get rid of some of this. So this is going to prefer to occupy an sp3 orbital, whereas this one is going to be in a pi orbital. Another way to think about these two molecules is to think about their conjugate acids. So if molecule 1 were to act as a base and react with an H+, this lone pair comes in and attacks, the molecule that we would be left with would look like this, with the hydrogen here. If molecule 2 were to do that same reaction, we would be left with a 7-membered ring. Oops. Sorry, that doesn't look very pretty, but 7-membered ring, and again with the hydrogen, where the lone pair used to be. So now comparing between these two molecules, molecule 1 went from aromatic to non-aromatic, and again this is non-aromatic because this position is no longer, it no longer has a delocalized pair of electrons. And this one went from non-aromatic to non-aromatic but more stable because it no longer has that localized carbanion. So molecule 1 lost a bit of stability because it went from aromatic to non-aromatic, whereas molecule 2 gained stability because it went from non-aromatic with a localized negative charge to non-aromatic without a charge. So all of that being said, the way that I graded this question was you got 1 point for indicating what was the correct molecule here, which was... So you got 1 point for indicating that molecule 2 is more basic, and then you received a point if you explained something regarding why molecule 1 is not favored to be a base, and something explaining why molecule 2 is favored to be a stronger base. So you needed to have an explanation of both molecules, not just one or the other. So you couldn't just say molecule 2 is more basic because it's anti-aromatic. You had to say molecule 2 is anti-aromatic and molecule 1 is aromatic. So the aromatic prefers to keep its aromaticity, whereas molecule 2 prefers to get rid of the carbanion and become more stable. Question 3 says, below draw the electrophilic aromatic substitution reaction between benzene and Cl+. So for this mechanism, so benzene and Cl+, for the mechanism, one of the doubles is going to come out and attack the chlorine, which is an electrophile. So benzene's the nucleophile, chlorine's the electrophile. When it attacks, we are left with a chlorine on one side of the double bond and a positive charge on the other side, because this carbon here lost one of its bonds, so it's now a carbocation. And then to restore aromaticity, some sort of base needs to come in and deprotonate at the chlorine's position. So this chlorine has an invisible hydrogen, and I'm just going to use Cl- as the base, but you could have used any generic base, and show that the hydrogen here is deprotonated, and then the electrons that were bonded between the carbon and hydrogen are going to collapse down to restore aromaticity. And the way that I graded this was you received a point for showing the benzene attacking. You received a point for the correct intermediate, and then a point for each of the curved arrows here, and then a point for the final product. So this was worth 5 points. So that's the end of the free response. If you have any questions about what I've shared here or the way that I graded your individual assignment, feel free to reach out, and I'm happy to answer any questions.